So we've successfully graphed a single inequality statement. What happens when we put two of them together to make a system? What we're looking for this time is the set of all points that satisfy both inequalities at the same time. So to help us out with this, we're going to do a little bit of labeling just to help us. So this is going to be A and this will be B. So for A, we're going to come in and find the intercepts. And again, I'll do the cover-up method. So if we come in and let y be 0, 4x is equal to 12, so x will be 3. If I let x be 0, then 3y equals 12 and y is equal to 4. So my first line, solid this time, so we'll make that note also, solid, cuts through positive 3 and positive 1. And normally I'd worry about shading it. What we're going to do instead is we're still going to pick the test point of the origin. When we plug that in, we'll get 0 plus 0 greater than or equal to 12. Again, 3, 4 times 0, 3 times 0 is still 0. So this is false. So that means we don't want to include the test point. Now, instead of randomly shading like this, because it gets more complicated, what I'm going to do instead is put arrows on the end of it, indicating I'm going in that direction. And that's line A. So this represents A. I'm going to go ahead and do line B in a different color just to help us keep track. You can see the colors, this will be in blue. So now let's take a look at B. Well, B is x minus y is less than or equal to 0. If I go to try to find the intercepts here, I'm going to get 0, 0, and only 1, which doesn't help in graphing it. So we're going to use the slope intercept method. We'll isolate the y. So let's see, negative x. I'm trying to do too many things at once. So I have x minus y equals 0. X is equal to y. So we can see that we've got that slope of 1 again. Going through the origin, up 1 over 1, up 1 over 1. Still solid because of the inequality from the beginning. So it comes through and does this. Okay, to test that one, let's use that 5, 0 again. It's a nice number, it's over here, right? So that would be 5 for x minus 0 for y, and is that less than or equal to 0? 5 less than or equal to 0 is false. So for the blue line, I do not want to include this test point. So it's going to go in this direction. So I've successfully graphed both lines, but now I need to find the one region that satisfies both of them. So I'll do this the long way one time. If I were to shade this kind of triangular shape down here, that would not work because neither the black line or the blue line are pointing towards it. If I shade over on this side, the black line, A, is pointing towards it, but the blue line is not. Opposite problem over here, the blue line points towards it, but the black line does not. So the only region that satisfies both inequalities is this region up here. So instead of an entire half, it's only a quarter of the board. This is what we consider to be an unbounded region because the top part of it's not bounded or closed off. So if you were inside of here as a piece of molecule, a bubble or something, you could escape out of it. So it is an unbounded region. Let's try another example of a system. We're going to add a few more inequalities in. There's a lot of bookkeeping going on here, and the better you are at bookkeeping now, the easier it will be the next time. So example 3, our system of inequalities, says x plus y minus 6 less than or equal to 0. 2x plus y minus 8 is less than or equal to 0. And then we're going to tack on x is greater than or equal to 0 and y is greater than or equal to 0. I'm going to label them again just to help me. So this will be A. The next one will be B, and I'm going to graph it in blue. And the last two down here, C and D, they actually form our axes. So if you think about this, x greater than or equal to 0, everything that's in terms of x that's positive is on this side. So there's C. D are all y values that are positive. Well, all y values are positive are above. So right now we know we're in the first quadrant because the other three quadrants don't satisfy both of these two inequalities. So we're stuck in the first quadrant, which makes sense in the real world. You wouldn't have negative quantities of goods being produced or negative costs associated with making something. Okay, let's go look at A. So A was x plus y minus 6 less than or equal to 0. So I'm going to treat that as x plus y equals 6. Again, it'll be a solid line. We know that the intercepts when y is 0, x is 6. When x is 0, y is 6. So it's going to cut through at 6 and 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And all we have to do is test it to see which way we're going to shade it. I'll use the origin. So is 0 plus 0 minus 6 less than or equal to 0? Notice that when I test it, I always go back to the original statement, not something that I manipulated along the way. So negative 6 is less than 0, so we know that that is going to point towards the origin. Okay, B. We have 2x plus y minus 8 less than or equal to 0. So again, I'm going to make that into 2x plus y equals 8, just to make it easier. So finding our intercepts again, we'll let y be 0. Solving 2x equal to 8 gives us a y value of 4. If we let x equal 0, then we'll get y equal to 8. Again, solid because of the inequality. So positive 4 on the x-axis and positive 8 on the y-axis. And there's line B. So we've now graphed all 4 inequalities. We just need to satisfy them, find the one region that satisfies all of them. So we do this kind of guessing game. We know this out here is no good because neither A or B are pointing towards it. Same thing with both of these. Either one is pointing towards it, but not the other one. So the only region that satisfies everything in the first quadrant is this trap. I don't know what to call it. It's quadrilateral. It's 4 sides sitting in there. And it is bounded. It's bounded because if you were a bubble trapped in there, there'd be no way you could get out. So it's a bounded region. So you now have seen an example of an unbounded system of inequalities and a bounded system